All right, so we learned how to handle exceptions, to some extent at least. Now, what I haven't shown you yet is how to differentiate between the different exceptions. So here, we always printed out this message divided by 0, even though it was a conversion error that occurred. So we need to test for specific exceptions to differentiate what's going on. And so I've already shown you the syntax. Here's an example of that syntax. So now I have multiple except statements. And in every except statement, I specify which exception I want to handle in the following code. So here you'll see if a zero division error occurs, I have a specific message for the zero division. If a value error occurs, so this is the value error occurs in the string conversion. So then I handle that differently. And then finally, in all the other cases, I just print out a message, I don't know how to handle this. Okay? So now you will get an error message that is specific to the error that actually occurs. So this is in principle a valid, the conversion here is valid, but the division isn't. If I had a string of 1, then everything works. And if I have an invalid number, then I get a value error and with the associated message here. Now if I only handle the zero division error, so if I remove this part of the code, and only handle the zero division error, then you will see that this exception is not being handled by our program, and therefore the program will crash, and we will see the same value error that we would see if we didn't do any exception handling. Right? So in this case, we only kind of catch this case where we actually divide by 0 and the conversion works well. So you can also, this is just to make the syntax more convenient, you can handle a bunch of exceptions in one code block by just providing a set of exceptions. Now, if you're interested in which exceptions are actually out there, they're listed here on the web page, or you type in $!error to get all the classes that end with error. So all the inbuilt Python exception end with a name error. And you'll see there's loads of them. So depending on which type of, so you see there's some connection errors. So this is probably if you do some networking stuff, and so on and so forth. Okay, so the reason why I show this list is because sometimes we want to raise exceptions as well. Right? So maybe in our program, if we hit kind of a special point, or maybe the user passes invalid data, right? Then we would also want to, the program should actually raise an exception. And the way you do that, the syntax is you write, the syntax is simply raise, and then the exception that you want to raise. In this case, I decided to raise an index error. And then the first argument is always an error message that describes more detailed why this exception was raised. And so now, of course, now it is important that you have a list of all the exceptions that are out there. So you can just check that list to find a relevant exception that is useful for you. So in principle, I mean, which exceptions you raise is completely up to you, but you should choose one that is meaningful. Right? It doesn't make sense to raise an index error if the problem is that you can't open a file. So one one use case that one sometimes sees is that one has a specific code where an error might occur, and then you handle the exception, print out an error message, and then you raise the same exception again. So here the idea is that maybe you're inside your program somewhere, and you know that an error occurs, but you don't want to handle it quite yet. You just want to provide the user with some information that there's a problem. But in that specific part of the program, you don't actually know how to handle that problem yet. You just want to inform the user. So in this case, what you do is you wrap your code into a try statement. Then you catch, in this case, let's say the zero division error. Then you print out the message that you want to, in notification to the user. And then you raise the same error again. So this SE here, this is the exception object that has been raised. And so I just raise exactly the same exception object again. So this is a little trick that allows us to add additional information when an exception is raised. So we can try this out. If I call this, so you see this double invert, actually it works when I call it on 1.1. So then it behaves as normal. But if I add 1, then you see x, here we're trying to, the formula is 1 over x minus 1. So if I choose x equals 1, then we will have a zero division error. So now the behavior is that we get some nice information about the error, that we choose kind of an invalid range or invalid values, and then the original exception is still being raised. And maybe it should be handled in a different part of the program, but I don't know quite yet how I should handle here in this double invert part. So this comes to the next part. So what happens now if you're in a big, yeah?
Could you add the print to the exception? Because you just do a print every time you are doing a big project, you want to add print everywhere on the project. Could you add it to the raise object, to the exception?
Right. Yeah, good question. I think I'm not entirely sure, but you might be able to do something like this. But you would have to look this up. But you can probably access so each exception has a message, and you can probably extend that message with your own data. Yeah, there might be another way of doing it. Okay, so one interesting aspect is if you have a larger program, which is kind of a nested program. So you have a function that calls another function, that calls another function, that calls another function, and then inside there, an exception is being raised. Right? And so now the behavior of Python is that if this exception isn't handled in this lowest function, then the function execution is just being stopped, and the exception is basically passed upwards to the next higher level function. If that exception isn't handled in that function, it's being passed on again to the next higher level function, to the next higher level function, and finally, if you're in your main program and it's still not being handled, then the program stops, and you will see the exception error on your console.
As Python handles errors, even though you don't have try catch, does Python internally do your whole code in a try exception?
I didn't get the question.
So if you don't have any try and exception in your code,
Yeah.
you still get the exceptions back. Does
Yeah.
that mean that Python internally does a try on your entire code and then accept the exception? Because you still get errors even though you don't try and accept them.
Yeah, but so the execution is immediately stopped at that point. So Python really cancels your execution. I guess you could see it as that your entire program runs in a try except, and then it just prints out if any exception occurs, then it just prints out the error message and stops the execution. You could.
Doesn't exit,
Well, it does exit. It does exit, yeah. So, yeah. So if you want to, so imagine you're writing imagine you're writing a Python program that controls the, what is this called? A heartbeat maker? Pacemaker, thanks. Right? So for a pacemaker program, right, you really don't want that the program just stops because an exception is being raised. Right? So for these extreme cases, right, maybe you should actually wrap your main program into a try except code block, and then in case any exception occurs, you just restart you just call the main function again, so that it just goes back into it just restarts itself, right? So that could be, I mean, please don't write a pacemaker in Python, but I mean, this is maybe a little bit what you meant. So you can play around and make your program more robust. But, I mean, really, you should fix the underlying problem that is handling. But sometimes it's quite difficult if you, let's say maybe you're downloading stuff from the net, or there's some timing issues. It can be very challenging sometimes to figure out exactly all the details. And sometimes maybe it's best to just start from scratch. Anyway, so in these nested cases, exactly. So here I have an example where I call divide list. Okay, so divide list internally calls divide string, and then divide string calls divide, which is implemented up here. And so divide something by x. Right? So now, if I have a number that is 0 in here, then I get a 0 division error, and I get it at this point in this line up here. Right? And so now I have multiple options where I should handle that. So I could handle it either here. So I could wrap this code block in a try except. Alternatively, I could handle the error up here in the divide string method. Or I could divide it here in the divide list method. Right? Or I could actually handle it in the main program. So, and depending on how, so I don't think there's actually a good answer on where you should do it. It's problem specific, and so I just want to inform you that you have multiple options on where these errors are being handled. Typically, I try to handle them quite late. So I typically raise errors, and then I pass them up quite high before I actually, except if I can fix them. If there's kind of a simple fix, then I handle them immediately. But if I'm in a function, I don't actually know what is a good way of handling that, then I just pass it on and make sure that a higher function handles it. And so finally, in particular, if you have bigger programs, it's often quite useful to have your own exceptions and to essentially have exceptions with nice names that fit to the type of errors that you see in your program. And so it's relatively easy to create them. You just create a new class with the class name is the error name that you would like to have, and you just derive that class from base exception. And then I typically overload the init function, and so my init function typically takes the message with the information about what this, so when I initialize the exception, then I get this message object here, and I store it as an object class, and then the string representation implements what should be displayed when the exception is being printed out to the console. Right, and so then here's a simple example. So I just raise. So this is how you then raise your own errors. You just write raise my error, and you can provide a message. And then in the same way, you can catch your own errors as well with except statements. Yeah. Let's see if this works. Yeah. So if I execute that, I get this message. My error occurred with error message. Something went wrong. Okay, so now coming back to so we've got this big project, right? Where's our big project? Here, the Monty Hall game. And we wanted to handle errors, and so I decided to do that. How did I do that? Let's go here. Monty Hall game. So these errors, I decided to implement them only in the core functionality. So the user interface, there I didn't. No, sorry. So the raising the errors and the error definition happens all in my main package, where I also implemented the logic. And so essentially what I decided to do is I created a new exception type. I called it invalid game input, because that's typically the most common error that occurs. And I mean, the implementation is very straightforward. It takes in a message, and then I just print out the message again when the exception is printed to screen. And so then in my package, in the Monty Hall game class, I went through the program, and whenever there was something, whenever the user provided some data, I made sure that it's in the right range, and then I erased it if it wasn't. So here you can see the if the door is outside the range 1 and 3, then I erase an invalid game input. Or if the user tries to open the door that the host has already opened, then I erase an invalid game input, and so on. So I just went through my program and raised errors when I thought it's sensible. And so then in the command line interface, so here I was really lazy, so I just wrapped the entire game into a try statement. So now everything in here, because this invalid game input can occur essentially in every single step here. So that's why I decided to just wrap the entire thing in a statement. And then I catch these errors. So I say accept invalid game input. And then if that's the case, then I just print out the specific error and restart the game and say, well, you try to cheat, so you have to start from scratch. Yeah? Okay. What comes next? Yes. Next is adding tests. So for tests, you already learned that PyTest is a common testing framework, and this is also what I used here. So essentially, I just added a new folder called tests, which is a good practice to kind of separate the tests in a separate folder. And then, so kind of a good structure is also to have for each module in your package, you have one test file. So in my case, it would be test montyhallgame.py, for example. And then in that file, I implement all the tests for that specific module. So I want to show that to you in this. There we go. So what do? So this is just a bunch of functions, right? And they always have to start with this test underscore name so that PyTest can recognizes it. And so the main thing that I want to mention here is that it's often good naming convention to name these tests meaningful. Right? So here I test that game wins or loses. Right? So hopefully by just reading that name, you should have an idea on what this test does. Right? So it plays a game with some random choices here, and it checks that at the end of the game, we've either won or we have not won. That's, okay, so these tests are maybe not so, they're really basic. But then here I test that selecting invalid or raises correct exception, right? So in this test down here, I try this, I have a try statement, and I actually make sure, so this is kind of a negative test, right? I make sure that it crashes when I put in invalidator, which is also something useful to test, right? You don't want to program to just accept invalidator. Actually, so this is maybe not such a good. Yeah, so this is not a good test actually, because what happens now if my program was wrong and it would actually not raise an invalid game input? Right, so this test would still this would still just pass. So, well, the only time when this test will fail is if a different type of exception will occur. Right, so that's really the only thing that I'm testing here. But if the game select door number 4, right, that's an invalid input, right, it should really crash. But if it doesn't crash, then this test will just run fine. So I should really have something. I'm not actually sure what the syntax is. Ideally, I need something like an else statement here. So I want to type in return assert false. Ideally, I would like to have something like this, where if no exception occurs, I want this test to fail. But I'm actually not sure what the syntax is, but just as a comment. Well, anyways, and then I added another test here to check that the statistics don't work. Yeah. Okay, so you add your tests, and then you can run them. So you know with Python -m pytest, and then the directory file. And if you do so, fair enough. So I've checked this before, they all pass, which is great. Good. So now we have documentation, we have kind of a clear structure, we have tests. The last thing is to make our project easily installable. And there are kind of two components for it. So the first component is that your project might have some dependencies. So we need to make it easy. We need to make it easy to install these dependencies. And then the second component is the installation of your project itself. Now for dependencies, the standard way of doing this in Python is to add a file requirements.txt in your main project folder. And that file is just simply lists, it's just a normal text file that lists each package name in a new line. And so in our case, our Monty Hall game depends on Flask, which is the web interface, and on PyTest for the testing, and on Sphinx if you want to do the Sphinx documentation. So my requirements.txt file simply consists of these 3 lines, and these are kind of the standard package names that you would also use when you typed in pip. So if you do pip install, then you use the name Flask and PyTest and Sphinx. And so essentially now, if you want to install all the packages, all the dependencies for your program, all you need to do is, what you need your users to do is to type in pip install -r, and then this requirements.txt file. So yeah, and that will go through all the packages listed in that file and install them. So this is also really good practice for yourself, because if you have many dependencies and you look at this, you want to use it a year later and you forgot what you need, it's really useful to just have these requirements and then installation instructions that you know how to get it up and running again. Yeah. Yeah, so you can actually do that. I'm not entirely sure, but you can specify version numbers, and you can even point it to GitHub repositories. So sometimes these packages are not available on, if you make your own package, for example, it might not be available on this as an official pip package, but it will be somewhere on a GitHub repository. And if it has the setup.py file, then you can which means that you can install it using Python setup.py. And then you can just, as a line here, you can just point it to that GitHub repository, and it will install it the right way. Okay, so that's the dependency. So now the setup tools. So this is this is also a standard file that every bigger project has. It's called setup.py. And it's the standard way of how to install packages, your own packages. And so essentially, the file just consists of, I don't know, 15 lines of code. And it always looks roughly like this. You just import this setup function here, and then you call it, and you need to provide various information about your package. So for example, you need to provide a name, a version, then the author, a description. But the most important parts actually are the ones down here. So down here, you specify which directories should be installed on your system when you install this your package. And so in particular, there's this option packages equals, and this is a list of directory names, and all these packages will be copied over from your local directory into the system directory. So essentially, because I want to have, later on I want to be able to type in import Monty Hall game, right? Monty Hall game was this package directory. That's why I added in here. So this is really a directory name that I specify here. The second important part are these executables. So the ones that will be available not as modules, but as really command line files that I can just, on the bash script, I want to be able to type in play Monty Hall CLI or play Monty Hall web, and it should just work. And this is what you do with the scripts equals. And again, it's a list. And in that list, you specify each executable Python file that you want to have available after the installation. So essentially, you create the setup.py file in your folder, in your project folder. And then installation is simply Python setup.py install or pip install dot. And so we can try this. Let's cancel this. So it's here. Okay, so here you see I have the setup.py. So now I do pip install Python setup.py install. And then I install it into my, I don't want to have it system-wide, so I use this -- user to only install it user-wide and not system-wide. And then you see there's now loads of stuff going on. It's compiling some of the stuff, and then, but here the interesting part is these lines here, for example. It's installing my two interface scripts, so these are executable scripts, into my .local/bin. Right? So now, so now essentially I can go anywhere. I can open up a new terminal, and I can type in play Monty Hall, let's say web. Oh yeah, that actually doesn't work. But let's say CLI. It also doesn't work. Oh, sorry, I shouldn't be in the. There was a mess up because I was still in the package directory. So I've now left. I now left the package directory, and now it works. So if I'm, yeah. Okay, so now these commands are just available and anywhere, well, if there's no collision with naming and so on, and then you can play the game. Okay, yeah.
In the setup.py, there is the possibility to add the dependency there. What is the difference?
Yeah, good. Yeah. So the question is, can you add the dependencies into that setup.py file, and that ideally they would just be installed alongside when you. Yeah, you know, I don't actually know if you can specify them in here.
You can.
Yeah, you can. Okay. So yeah. I guess that's a really good way of doing it. Yeah. So then, of course, once you've done all this, you should have an installation instruction. And so a typical name is that you just have this file install or install.txt. And in there, you describe how your package is installed. And so the most important things is that you install these dependencies, and then you install the package itself. Or if you do it the clever way, then then the dependencies will be installed automatically. So after all this, we'll have 3 more files. We have this install file, the requirements.txt file, and then the setup file. Okay, and this is how kind of the directory layout of a full project then looks like. So we have some installation files up here. We have the actual main packages and modules that we want that kind of provide the core functionality. So we have some exceptions here, and then the game logic is a separate module. Then we have some binary files up here that we want to be, that the user should be, that should be available through the bash later on. Then we have our documentation based on Sphinx. And then we have our tests written as in Python. And I think, so that's kind of a solid, if you have such a structure, then you kind of have a solid project structure that you can build on and expand. Any questions on projects? No? Yeah?
Something about the driving stage.
Yeah.
You add a cert inside that.
Or are you referring to my bad test? Yeah, but you know, that doesn't help because, so, okay, I can, instead of just passing, I can say assert, but now shall I assert false or assert true? Ah, yeah, that's a good idea. Yes, thanks. That's it, yeah. That's exactly it. So now I should never be able to come to that line. And if I do, then that's an implementation mistake, so I can call assert false. Good, thanks. Okay. Yeah, so I don't have so much time, but I wanted to show you one last thing that if you've actually used multiple times already in Python, but I've never explained what they actually are. And they're called decorators. It is this add symbol that you sometimes add on top of functions. Remember when you did number, you had this add chit, and also for Flask, you have the add route that you always add on top of functions. So I thought it might be useful for you to know what this actually is, and maybe you can even sometimes use it for your own projects and implement your own decorators. So I'll try to motivate it later on with an example because I think it's a bit theoretical first, but when you see an example, I hope it will get more clear. But the initial point where we need to start is that in Python, functions are just normal objects, and functions in particular can be passed as an argument to other functions. So for example, let's say I have two functions here, one add function that just adds two numbers and one sub function that subtracts two numbers. And then I can write a third function called apply, and that takes a function and then two numbers, and it just calls that function on these two numbers. Okay? So essentially, the apply, so here, right, the function is just passed in as a normal argument, but then inside here, I can call it, just if it was a normal function. And so the trick, if I do that, I can do things like apply add 1, 2, and the result will be 3 because I will apply the add function to the numbers 1 and 2 and up here. The same way I can now call apply sub 7, 5, and then the result will be 7 minus 5, which is 2. Okay? Yeah. So in the same way, we can nest functions. So we can, in one function, we can actually define a second function, and then so here, this function cube, and that this function cube will be available just as a normal function. I can call it as well. So for example, here when I call for G46, it will, it will basically run as expected. Okay, so that was even more crazy. We can build functions that return functions. So, and we can build functions that generate new functions and return them. So here's an example. So this H function doesn't take an argument, but it defines a new function, and this function, look, it's parameterized. It contains this parameter pi here, and this pi value is just hard-coded up here, but it is parameterized to this pi function, and then after the definition, I just return it. And so essentially now if I call H, the return value of H will be a function. And I can call that function down here later on. And so then what I get is, when you actually call it, you get this message up here with a pi value that was specified up here. Okay? So in a way, we can, in Python, we can even kind of construct, we can build functions that construct functions on the fly. And this is essentially the idea of decorators. So the idea of a decorator is that you take a function and you wrap that function inside an outer function. And the outer function will do some post and pre-processing or whatever. But it essentially will do some pre-processing, then call the inner function, and then do some post-processing, then return the result again. So the toy example up here is that, okay, so we have a function foo, and we want to decorate that function foo so that when we call it, actually something happens in addition. And this, what happens in addition, is implemented here in the outer function. So essentially, our outer function implements the new behavior here. So our outer function takes a new function, which will be this foo, and then it will generate a new function that implements the behavior of our decorated function. So in particular here, in this case, I just decide, okay, I want to print some additional messages before, and then I call the original function and return the result. And so I've generated on the fly a new function, an inner function, and my outer function then returns this decorated function. So I know this might be a bit convoluted at first, but you'll see some applications. But essentially what I can do now is like the way I use this now is that I define a function, and I apply this function, I use this outer function here and apply it, and I get a new function out. It's a decorated version of foo. And this decorated version of foo now behaves just like foo, right? It returns 1, except that it also does some additional stuff before it prints out something to screen. So let's look at a slightly more useful version of this. Suppose you kind of have given a function, or maybe you imported somehow this f function, and it computes the logarithm of x minus 2. Now, this function works well for many inputs, but it does not work for minus 1, because, so it works for 5, but it doesn't work for minus 1, because the logarithm of minus 1 isn't defined. So then it just crashes. So let's say we would like to let's say we want to implement a decorated way of that function that automatically limits the range of values that we can apply it on. And so the idea is now that we implement this check range function. It takes our original function in here, and then the annotated or the decorated version of that function is now, first we check if the input is smaller than 0, And in that case, we just print that this is not a valid input. But if x is larger than 0, then we return, then we call the original function and return its return value, because then we know things is going well. And so this check range function is now our function generator that generates these decorated functions. So the way I can use this now, I just take my unsafe function f, pass it into my check range function, and get a new decorated or a safe f version out. And now I can call it on 5, and I can call it on -1. And if I call it on -1, I now don't get a crash anymore, but I just get an out of range error message. Okay, and so it's exactly this idea that the decorators implement. And it's essentially just a shortcut of what I've done up here with this f check equals check range. So essentially, and then the syntax is simply you use the add, and then you use the function name that you want to have as a decorator applied. So now, if I have a function g, and I know this function g is unsafe for some inputs, so now all I need to do is I add this add check range, and now the function will be automatically wrapped with my check range function, which means that if I apply it to 0, it will give me my out of range message. If I hadn't this decorator, I would get a value error. Okay? Okay, so maybe I'll show this. Yeah, I can motivate a real use case for a decorator. Imagine you have a function that is really, really slow. It takes in two inputs, x and y, and it just takes forever. Maybe you're downloading huge files or something, and then it gives you some results. So I'm simulating that by just having a sleep in here to simulate that it's a slow function. So I can time it, and if I do that, right? Okay, so this function takes 1 second roughly, and not so surprisingly because I have this sleep one here. Now, memorization is an idea that we remember the inputs of a function and the outputs of a function, and we cache them. And if we call the function again with the same inputs, instead of calling the slow function again, we just use the value from the cache and return that. Okay? And so this is exactly what I've implemented. It's a memorize function that it takes in a function, and then I have a function generator implemented down here that implements this caching. So essentially, whenever that function, this decorated version is called, I first check. I have a dictionary with all the input-output values that have been called before, that I've collected before, and I first check if this input values if they're already in my cache, and if so, then I just return the cache, and otherwise I call the function, get the result, cache the result down here, add the result to my cache, and then return the result. So in a sense, that's kind of, and that's a widely used way of memorizing. Is kind of quite a standard technique. And so now, if I now take my slow function and I add this memorize decorator, right? It's just one. Okay, I should implement it here. So now I've implemented it, and I can use this memorize decorator. And if I time it now, you can now see that it takes 1 second per loop. Yeah. Okay, let me try this. So now if I have slow 1, 2. Okay, so the first time it's really slow, but now if I call it again, right, it goes really, really quickly, because now I'm just relying on my cache. Okay, 1 minute before 12. Now it's 12. See you next week.